All right, so continuing our last lesson, let's assume that we have a spinner where you have more area assigned to 1 rather than 2, so that the probability of getting a 1 is 2/3, whereas getting a 2 is 1/3. Okay, so if you're in this situation, let me ask a few questions. So first question is, uh, what's the probability of getting, no, I wanted to say, what is the sample space when spun twice? Okay, so let's think about that. Now, if you spin this twice, what possible events can happen? You could get, yes? Right, in the first one, you can get a 1, and the second one, you can get a 1. That's like one possibility. You may get 1 in both spins, okay? All right, what else can happen? 1 and 2. What else can happen? 2, yeah, 2 and 1, and then 2 and 2. So that's the entire sample space, okay? Now, last time I was talking about rolling 2 dice, right? Here, it's a bit different because when you roll 2 dice, the probability of getting a 1/1 or 6/6 was all the same. They were all 1 out of 36, right? However, here, you should see that getting 2/2 is much harder than getting 1/1. Do you agree? Because there's more chance of getting a 1 than a 2, right? Okay. So let me try to ask the following question, see if you can answer this one. What is the probability of getting 1 and then 2? Okay, so first, the probability of getting a 1 is? Yeah, it's 2 out of 3. And the probability of getting 2 is 1 out of 3. So in the first one, you would have 2/3, and the second one is 1/3. And here is where you have something called the multiplication rule. And it goes like this. If 2 events don't affect each other, and the more technical terminology for this is if the 2 events are independent, and certainly the second spin is not affected by 1. It's not like if you spun the first one and you got a 1, and in the second spin, the spinner it doesn't have a mind of its own. It just doesn't care if the first spin was 1. It doesn't say, oh, you got a 1 in the first roll, so I'll increase your chances of getting a 2. It doesn't work that way, right? So the 2 spins don't affect each other, right? In that case, we say the 2 spins are independent, okay? 2 events are independent. And in that case, the probability of both happening, and actually that's the important part. It's the word and, okay? Right here, and. Right? And is multiplication of probabilities. Okay? And so the answer to that would be the probability of getting a 1 and then 2 in this probability space, getting a 1 and then getting a 2, is probability of getting a 1 in the first one times probability of getting a 2 in the second one, which is 2/3 times 1/3, which is 2/9. All right, so seeing that, I want you to think about the probability of 2, 2. What's the probability of getting 2 and 2? Yes? 1/9, because getting a 2 is 1/3, another 1/3. They are independent, so you multiply them, you get 1/9, right? How about 1, 1? 4/9, yeah, right. It's 2/3 times 2/3, so it's 4/9. And 2, 1 would be 1/3 times 2/3, so there will be 2/9. Okay. And once you figure that out, this is 4 9ths, 2 9ths, 2 9ths, and 1 9th. Once you figure it out, then make sure that the sum should become what? Sum of all the probabilities must be 1, right? And you're right. You said 9, but it's the numerators add up to 9, right? 4 plus 2 plus 2 plus 1 gives you 9, and 9/9 is 1. So you do get the entire probability space probabilities adding up to 1. That's a must, okay? If you don't get a 1, if you get a number that's something less than 1, that means your sample space is not complete. There is some other occurrence that you forgot to list. Or another possibility is you just simply made an error in adding. Okay. All right. Now let's move on to the next question. What is the probability? What is the probability of getting sum of 2 spins to be 3? Okay. So you get 1 spin and the second spin, and you want the 2 to add up to 3. What do you think the answer is? Yes.
I got 4 9ths.
How did you get 4 9ths?
Because the spin 1 2 was 2 9ths, and spin 2 1 was 2 9ths, and I added them together.
That is correct. So you just said getting a 1 2 is 2 9ths, getting a 2 1 is 2 9ths, and if you think about it, how can you get 3? It's either 1 2 or 2 1, right? Okay. So here there's another important rule, which is called the addition rule. If 2 events don't overlap, okay, and the technical word for that is if they're disjoint. If 2 events are disjoint, the probability of or, and once again, this is the important part, or, okay, or is sum of probabilities. And likewise, the answer would be that you take, what is it? You take probability. Let's just say y is the sum, okay? The sum, right? So the probability of getting y equals to 3 is actually probability of two events. It's either 1, 2 or probability of 2, 1, right? Yeah, these two, and you have 2 nines and 2 nines, and you add them up. Okay. You know, this will be much more exciting if we had a session doing gambling. If we like had you guys had to pay $90 and you had to spin the wheel, and we might have like different prize money for this combinations, and it will look much more exciting. Right now, it's it doesn't look that exciting because it's just numbers, but just imagine that. Yes, you have a question.
In the school year, you want to take us to a casino?
Huh?
Take us to a casino in the school year.
What?
Take us to a casino.
Oh, yeah, yeah. Like we could have a casino trip, field trip. Like we can explain to the school that it's part of statistics education, right? Okay, yeah. Unfortunately, I don't think it's gonna fly. Uh,
They give us an $1,000 loan.
$1,000 loan for statistics
Instead of
education.
giving
Yeah.
like out to bachelor stuff, we give it for
All right. Okay. All right. Now, here, important stuff. Expectation values. So let's just think of the y, the sum, as actual dollars. It's not much, but let's just think of this as $1, $2. So you might have this would be what? $2 would be $3, $3, and $4, right? And you want to know how much money you're going to get. Okay, yeah. And again, if you want to think of this as something more exciting, just put something like million there. Like it's like $1 million and $2 million, and suddenly it gets more interesting, right? Okay. So what is the expected value when you spin this thing twice, right? So that is written like this: E of y. Okay. And the way you compute this would be simply you add them up, okay? And you take the values that y takes and multiply it by the probability of that happening. Okay? So let's think about what that is. So what's the least number that y can have? No, that's x when you spin just once. Y is spinning twice, right? So if you get 1 and 1, then how much do you get? 2, right? So you get 2. 2 would be when you have 1 and 1, right? That's 2. Right? What's the probability? 4 nines. So you put 4 nines. Plus, what's the probability of getting 3? Right. So getting a 3 is 4 nines. And then getting a 4 would be 1 ninth. And you add them up. So that's 8, 12. 12 plus 8 is 20. Plus 4 is 24 over 9, or it's 8 over 3. Top and bottom are divisible by 3, so I divide it by 3, and you got 8 over 3, which is about $2.66, right? Yeah. Yeah. So it works like this. Like, uh, let's say uh, each number represents $100. Okay, I think that's like more reasonable. And somebody asks you to play this game, and you get 2 spins, right? And the price for the 2 spins is $300, right? Yeah. Would you play this game? The answer is no, because this is a 2.67, right? You get about $267 on the average if you play this over and over, okay? That's the expected value, right? because I'm thinking of 1 as 100, so you have to multiply by 100, right? So it'll be 267. So you'll be losing about $33. Yes.
I'm just a little confused though. I get these values from like 4 9 and 1 9.
Oh, these are so I already have the question. Getting a 3 has the probability of 4 ninths, right?
Right.
So I multiply 3 by 4 ninths.
Okay. So when you do that, are you like mentally like making the chart from like the last class where you have like all of like
Okay, so the question was, when I do that calculation, am I mentally making a chart? And actually, you got me there, right? That's actually good. All right. So I explained the chart last time, and so uh, a better way, if you're okay with this solution, that's fine. But sometimes you do get confused, right? And in that case, what you want to do is you want to make a chart of possible values and the probability. So if I made the chart of the y value and the probabilities from here, getting a 2 is just this one, which is 4 ninths, right? So you put 4 ninths. Getting a 3 was some of these two. Again, it was 4 ninths. And getting a 4, you can get 4 only by getting a 2 and then another 2. So it'll be 1 ninth. Right? So you can make such a chart. Then calculating the expectation value is much easier because all you have to do is just multiply, multiply, multiply them, add them together. Okay, so that's the expectation value. That's how you do it, right? So according to here, you multiply 2 times 4 ninths, multiply 3 times 4 ninths, and you multiply 4 times 1 ninth. You add them up, and you get 8 over 3, just like before. Okay, so that will be another way to do the same thing. Okay, thank you for that question. All right. Yes.
So I just have, so like a question would be, what's the expectation value?
Yeah. So a question like this will be a nice question to be on the exam. You like question. You could have a question where it asks you to write down the sample space. I might ask you like, what's the probability of this one or some combination of things. And at the end, I might be asking you the expectation value. That would be a perfect question to be on the exam.
Give us the formula.
Yeah, but I mean, okay. So the formula I would be giving. So the question was, will I be giving you the formula? Yes, but formulas are really not very helpful if written in this way. So the formula for an expectation value of a probability random variable x. So the probability of no expectation value of a random variable x. The formula is sum of xi pi. That's all there. That'll be it for the expectation value. So, I mean, it's not very helpful if you just see that, you wouldn't know what to do. So it's better to do examples and make sure that you understand what it means.
Because also like the expectation value, is that just like what does that really tell us?
Okay, so the question was, what does the expectation value tell us? Okay, so it's the okay. So first of all, expectation value is the weighted average of all the outcomes, weighted according to the probability. So you know how when I said what's the weighted average of xi? So let me tell you what so if you have say x and frequency, and you have x1 and frequency 1 and x2 frequency 2, so on and so on, then the weighted average of this was simply the average of x is you add up all the xi's, but since xi's are repeated by fi's, you multiply these two, and then you divide it by the sum of all the frequencies because that's how many items you have. So that's called the weighted average. You remember this? Is that good? Right. So actually our quiz that we just took, has this type of question. The last one, I was asking you to find the average, and it's really the midpoint value times the frequency. You have to do that, and then you have to divide by the total frequency, which was 50. That was a quiz question, right? So you probably know what this means. But look at this and see how close these two are, right? Right? They're basically the same, except that this one has sum of FIs divided. Here, I don't have that. But what if I did have it? What would this be? Can you tell me? What's the sum of all the probabilities? 1, right? So does dividing by 1 do anything? It doesn't. So actually, this expectation value is exactly this one. It's just that because we're using probabilities, not frequencies, this division by sum of probabilities doesn't do anything. Yeah, it's not needed. Adding the probabilities will give you 1. So it's not needed. All right. So what does that mean? That means it's the weighted average of all outcomes. Now, why is that important? That's another question. And the answer to that is that there's this thing called law of large numbers. So that if you did this spin game, if you play this for a million times, and you divide it by the million of the prize money that you get, it will be pretty much this value. It will get closer and closer to the expected value if you do this over and over again. Okay, so that's actually a pretty important thing to think about. See, I'm mostly talking about gambling because it's kind of funny when you talk about gambling. It's exciting too, but when you're running a business, it also there are cases where it looks like a lot like gambling. It's like you're going with company A or company B, and there are different prices and there's different payoffs, and you have to figure out what's the probabilities for each. So you end up having to think about this. So in fact, after the statistics course, you'll be taking the Math 446, the operations research, which is running a business, and part of it uses these kind of arguments to come up with the best decision. You have another question? Yes.
If you said it can be, sorry, let me just rephrase that. If risk, if anything could be considered gambling, couldn't anything involving risk?
Yeah. So when you run a business, you always have unforeseen things, right? There's always a risk, right? As a CEO of, like, imagine yourself being a CEO of a company. You're making decisions, or you're in a managerial position. You're making a decision, and there's always risk involved. And often the best way to do it is to quantify the probabilities and think about what kind of expectation value you would get. And from there, you can kind of, like, if company A says, hey, we have this service, and we can cover you for this unforeseen events, right? Then you have to decide whether that company is offering a value or not. If they charge you too much, then it's not worth it, right? So it's exactly the same kind of case. Like you have you think about the probability, find the expectation value, and then if they charge you too much, then forget it, right? If they charge you much less than the actual expectation value, then it's something that you should do.
So could you use that in when you're buying insurance for a house or something like that?
Insurances are a perfect example. Okay, well, there's some other things, like it's not just expectation value. Sometimes it's like the variance. Yeah, well, it's a bit tough for me to explain all these other things. So let's just stop there. I need to go to another topic now. But it definitely you'll see the uses of statistics or probabilistic thinking as you work in everyday life. Okay. All right. So let's talk about counting. And here I want you to know two things: permutation and combination. Okay. So here's our first question. How many ways can you shuffle or permute is a more mathematical term. Okay, so can you permute A, B, C? And the answer is like this. You can do A, B, C, and you can do A, C, B. And if you think about it, these are the only two cases where you start with A. But then you could have another one starting with B, right? So you can have B, then it could be BAC or BCA. Okay, then tell me what two things that you would get if you start with C. CBA. I'll do CAB first, and then you have CBA. Okay. All right. This is important enough that I want you to take time right now to shuffle. Now shuffle or permute. I'll say permute, more mathematical. So permute A, B, C, D. Do it now. See if you can write all possible permutations of A, B, C, D. Now, one thing I want you to do is to write down the ones that start with A, and then you want to write down the ones that start with B, ones that start with C, ones that start with D. And by doing it that way, then you can compare how many you wrote. So, for example, if you wrote the ones that start with A and you have 6 of them, and then for B, ones that start with B, if you only counted 5 of them, then you're missing a 1 because they should have the same numbers. Okay, so try to organize so that you have one item starting all with A, and then B, and then C, and then D.
Does ABCD count as one of them?
Yeah, A, B, C, D will be one of them. Actually, I want that to be the first on your list. Okay. I'll be walking around, so you have to do the work. Okay. And to give you further hints, actually it'll be 6 each. So you'll have 6 of them starting with A, 6 of them starting with B, 6 starting with C, and 6 starting with D.
And we can't repeat any letters in there.
Hmm?
We can't repeat any letters. Like
You can't repeat any letters. Okay, yeah. All the letters must be used exactly once. This is like the sample space if you had 4 cards, A, B, C, D, and you shuffle them, and then you lay them down in order. So the order matters. That's what it is. Did anyone finish already? Oh, you did. Oh, you did. Let me check. Oh, that's good work. Very nice. You also finished? You have 6 of them. Yep, that's perfect. Very good. Okay. Yeah, I'm walking around and it looks like everyone's doing a great job. Okay, so please continue writing, and I'll also write. So let's see. No, just a minute. Did it wrong. It's okay to talk, but just remember some of your voices might be recorded. So don't say anything that could cause a problem. Now that's wrong. D, C, A, B, D, C, D, A. All right, good. So how many do you count? 24. You count 24, right? Okay. All right. So I want to talk about two things here. One is called dictionary ordering. So one nice way to make sure you haven't missed anything is to use a dictionary ordering. Like if these were words in a dictionary, you would think that BACD should appear before BADC, right? So if you order it that way, then you wouldn't miss anything. Secondly, there's another way to get it, which is by making use of a tree structure. It's like this. You could start with A, or you could start with B, or you could start with C or D, and then you have three choices if you start with A. You could start with B or C or D, right? And then if you have A and B used up, then there are two more choices. It could be A, B, C or A, B, D. Same thing here. It could be A, C, B or A, C, D. And finally, it would be A, D, B or A, D, C. And then the last ones, you only have one more choice because you already used three of them. So you can have A, B, C, D, A, B, D, C, A, C, B, D, and then A, C, D, B, A, D, B, C, A, D, C, B, just like that. And if you do it for the other ones, then there'll be another nice strategy to list all of them. Okay. Now, however, often when we calculate probability, it won't be that we need to list all of these. Rather, we would want to count how many there are. So here the real question is, how many are there? So it's about counting. And if the question was just about counting, then there's a way to get this without actually listing them all. Right? So to get it without listing them all, it would be like this. In the first slot, you can have A or B or C or D. So how many choices do you have? 4. In the second slot, because you already used up one of the letters, you're left with 3 letters, right? So how many choices do you have? 3. How many choices do you have here? 2. And then you're left with just 1 choice, right? And then here, there's a counting rule where if you do something and then if you do something, and again, the word is and, okay? Just like how I explained and in probability means multiply, here and will again multiply. So you want to multiply these, which gives you 4 times 3 is 12, 12 times 2 is 24, 24 times 1 is 24. So you get the 24 without having to list all this. Someone asked me to explain this again. It's like this. You have 4 choices. You can have A, B, C, D, right? And then once you use up the first letter, you have 3 choices. You can only have 3 for the next one. And then you have 2 choices. And then you have 1 choice. And because you're making a choice and, the word is and, okay? Then you have to multiply. What? Yeah. Yeah, so the question was, if it's A, B, C, D, E, what would that be? So ways to permute A, B, C, D, E. What would that be? 5, 4, 3, 2, 1, right? Just like that. and that'll be 120. So at this point, you realize that there's a pattern, right? So here's the important outcome, which is that permutations of n items, they're n factorial ones, okay? And n factorial is this. This is called 4 factorial. This is 5 factorial. You start with that number, you just decrease by 1, and you keep multiplying until you get 1. That's factorial, okay? It's not an exclamation thing. It means that you start with that number, and you keep decreasing by 1, and you multiply until you reach 1. Factorial. So this is called the n factorial. Okay. Oh, why did I erase this? That wasn't part of the plan. I did. Okay. I have to rewrite it. That'd be just too much. Okay. All right. So let me just write part of it. A, B, D, C, A, C, B, D, A, C, D, B, A, D, B, C, A, D, C, B. Okay. Now, let me talk about a slightly different question. So I didn't want to erase it. I forgot that I had to preserve it. But here are the 24, list of 24 things, okay? Now, here's a different question. How many ways can you permute A, B, C? So in this case, these two A's are not distinguishable, right? So you would have less, right? Can you think about this question? How many ways can you permute A, B, C? Interested people can actually write them down, all of them. It's not that many. Any ideas here? Hmm? Yes. 6, close, no, not 8. Any other ideas? So here's an idea. In this list, replace all the D's by A's. Okay? If I do that, then of all the 24s, they actually end up being some permutation of A, B, C. Don't you agree? Right? Okay. However, do all of these represent this different permutation of A, B, C? Does it represent different permutation of A, B, C? No. You can already see right here, right? They are the same. Oh no, they are different. Let's see. Oh, these two. This, no. Which ones are same here? A, B, A, C. Oh, this one you don't, but I guess you have to go to the next one. Okay, so if you have B, A, C, D, B, A, D, C, B, C, A, D, B, C, D, A, B, D, C, A, B, D, A, C, B, D, C, A. Okay, so no, not even this one. Oh, then you're gonna have. Okay, I see that it starts repeating when you get to this one. Okay, so C A B D, C A D B, C B A D, C B D A, C D A B, C D B A. Okay, and then I'm not writing that, but look at this one. So if you have like this, and then this one, this one, this one, this one. Okay, so I see that these two are the same, right? They both spell BACA. Okay, and BAAC, BAAC, these two are the same, right? And these two are the same, right? So it's not all 24 that represent different permutation of A, B, C, right? You see that there is a 2-to-1 correspondence. Do you agree? There's 2-to-1 correspondence. So here's a division rule. When things become indistinguishable, divide by permutation of those things. And here what I'm trying to say is that if you had 4 different items, 4 factorial is how many ways you can permute them, which is 24, right? However, since 2 of them are identical, AA and AA, when you change places, they cannot be distinguished, right? So the permutation of 2 objects, which is 2 factorial, you divide by them. And that's really 12. So you end up with 12 possibilities. Now, here's a very typical question that you might see in this section, which is, do you know how to spell Mississippi? Missippi, no, Ssippi, right? Okay, so question is, how many ways to permute? Okay, so if you permuted all this, how many ways can you permute it? And that's huge, but we can use the same kind of argument here, which is, first count how many numbers you have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So first it's 11 factorial. But then you have i's which are indistinguishable from each other, right? How many items do you have? 4. So you put 4 factorial for the i's. Okay, what else? 4 s's. 1, 2, 3, 4. So you divide by another 4. What else? 2 p's. And that's it. Okay. 11 on top was because I have 11 items to permute. So it's 11 with factorial. Okay, so 11 factorial, and you divide by 4 factorial, 4 factorial, 2 factorial, right? That's how you find all the permutations. Yes.
So the denominator, you multiply all the numbers together?
Yeah, I mean, if you take 11 factorial and divide it by 4 factorial, and then take this one and divide by 4 factorial, and take this one and divide by 2 factorial, that's same thing as this divided by the product of these two things, these 3 things, okay?
So what is so the I and for the factorial? Like what is the factorial?
Factorial means 11 times, 10 times, 9 times, 8 times,
Okay.
until you reach 1. That's what factorial means. Yeah, you have a question?
What about that? Isn't factorial the 11, 10, 9,
Yeah. So this is 11 times 10 times 9 times. You calculate everything, and you divide it by 4 times 3 times 2 times 1, 4 times 3 times 2 times 1, and 2 times 1. Yeah. You just calculate. And of course, we can't do it right here because it's just too large, but you can use a calculator to finish off. Okay. But that's how you calculate it. Okay. All right. So after you learn the division rule, then you're ready to learn two important counting methods, which are permutations and combinations. So first, permutations. This is a NPR, means number of permutations of R chosen objects from N items. So an example of this would be 4 permutation 2 would be like, think of, you have A, B, C, D, but now you're choosing 2 objects from here and permute. Okay, so if you chose A and B, it could be AB or BA, right? If you chose A and C, then it could be AC, CA. If you chose A and D, it could be AD, DA. But if you also chose B and C, it could be BC and CB. And if you chose BD, it would be BD and DB. And finally, if you have C and D chosen, it would be CD and DC. So you have a total of 6 plus 6, 12 objects. Okay? All right. So that's 4P2. And the way you think about this is like the following. Just think about the following. If I just permuted all of them at once, so you get 4 letters, which I erased. I wish I didn't erase that. We had a space where we had that. But if you have all the 24 permutations, okay, what you can do is you can erase the last 2. So if I have like A, B, C, D permuted, I can just erase the last 2, and you get something like this, right? But if I had this list of 24 and you keep erasing the last 2, then you end up seeing that some of them become, again, the same, right? So A, B, D, C, when you get rid of the last 2, these 2 will now become the same thing, right? So again, division principle works, and it's like this. You have, so the formula for NPR is you order the entire N, but because you're erasing the N minus R items, you're kind of getting rid of them. So in our case, 4P2 would be 4 factorial divided by 4 minus 2 factorial, which is 4 factorial divided by 2 factorial, which is 12 if you compute it. And this is really saying this. We are deleting the last two letters. Okay, so that's the formula for NPR. Okay, and then finally, combinations would be, people sometimes write NCR, but the more common notation is you put N and R like this as a matrix form. And the formula for this one is almost same as that one. However, the order doesn't matter here. So if you have 4 choose to, then A, B, and BA are considered the same ACCA are considered the same, ADD are considered the same. These are all considered the same. So you're dividing by the number of ways you can permute them. So the R factorial different ways you can order R items is deleted. Okay, so that's the formula for combinations. All right. Okay. You know, at this point, I've taught you so much probability that you probably have a hard time remembering all that. But let's do a quick review, and I'll mention the last topic. So the review would be that the things that you have to remember. Actually, some of the things that I said you don't have to remember. The important thing is so facts. Let me write down some facts. Okay. Number one, sum of probabilities. What do you get? 1. Number 2, expectation of a random variable. What is it? You add each possible value times the probability that can happen. Right? Okay. Number 3, NPR is n factorial divided by n minus r factorial. And number 4, NCR, or more like NR. This is the more prevalent form I'll write. And that's n factorial divided by r factorial n minus r factorial. And the important distinction here is that this one, order matters. But here, order does not matter. Okay. Now, with all the knowledge at hand, now I can introduce to you the most important thing of today's lecture, which is called the binomial distribution. So this format is like the sum of the two topics that we were talking about so far. Yes. Doesn't matter. Order doesn't matter. Oh, n factorial. Sorry, this is n factorial, r factorial, n minus r factorial. Okay. Okay, binomial distribution. So think about it like this. Very similar to the previous one. So you have 1 and you have 0. Okay. And we're going to repeat this. We're going to spin this n times. Okay. So let's think about this. If I say the probability of x1 means the first spin, of getting a 1 is p. This is lowercase p, right? Then what's the probability of getting a 0? 1 minus p, because the probabilities have to add up to 1, right? So this is 1 minus p. And we're going to name this as q. So that will be actually something important. So q equals to 1 minus p always. Okay. Now repeat this n times, and we're interested in the sum of the money we win. So either in every spin, we either earn $1 or $0. Okay. So x will be the sum of x1 plus x2 all the way up till xn. Okay. If that's the case, then the probability of getting x equals to k is given as n choose k, right, times p to the kth power and q to the n minus kth power. And this is called binomial distribution. You know, binary numbers are numbers that have only 1 and zeros. You heard of that, about that, right? In computers, they work with binary numbers. Here it's like either 1 or 0. So let's think about this for a minute, and let's see why this is true. First, if n is 4, and let's say k is 2. Let's think about that case. So what is the probability of getting x equals to 2? Well, there are many ways you can get a 2, right? So you can have, you can spin 1, 1, and 0, 0. That's one thing, right? So 1, 1, 0, 0 means 1 in the first spin, 1 in the second spin, and 0 in the next one and the last one. So your total sum of winning sum is 2. Okay. All right, give me another one. 0, 0, 1, 1, good. Give me another one. 0, 1, 0, 1. 1, 0, 0, 1. Okay, so it's getting a little long. But here's another way to think of it. There are 4 possible places where you can win or lose, right? But we just want the cases where you have 2 wins. So we're choosing out of the 4, we're choosing 2 locations, right? So the number of events that you have here, if you count them, this is exactly same as 4 choose 2. Okay, that's where this comes from. You're winning k times out of n, so you're winning n choose k number of times. Those are the the winning events are n choose k number of events. Okay. Now for each of these, what's the probability of p1100? Can you tell me? This is like getting a 1 and okay, 1 and 0 and 0. Okay, so if you have and, what do you do with the probabilities? Multiply. So to get a 1, what's the probability? P. To get a 1, probability is P. To get a 0, what's the probability? 1 minus P, which is Q. That's how we named it, right? And then Q, right? So you're going to have P wins, which means you're going to have Q losses. Is that right? Okay. So that's where this formula comes from. So each event would have this much probability by the multiplication rule. And if you count them, n choose k will be how many you have. Okay. So that is called the binomial distribution. So in the next class, I'll give you some examples that are really fascinating because this actually happens in real life not more than you think. Okay. So and then we'll talk about the averages from expectation values from here. We can also talk about variance and all kinds of things. So this will be very important for a few lectures. Okay.